Good morning, everyone. My name is Pen Su. I come from the TU Munich. Today, I want to talk about malware, which is how to evaluate malware detection system on graph structure. The name of my work is Manix. Today, we are reading a software which is full of the mobile device. Of course, smartphone is one of the most important mobile device which is used by nearly everyone around the world. Android is the biggest market share mobile operating system, and we can find many of the use cases about the Android operating system, like the smartphone, like the smart TV, and also the smart car. Unfortunately, with the development of the Android ecosystem, there are more and more attention focused on the Android malwares, which is touched like the 2.5 million samples in 2017, and the number of the malware samples for the Android device is also increased very fast. Like every 8 seconds, there is an infected Android application, and we can find like the 10,000 new malicious applications per day. And there is there is a image which showed in the first half year of the 2019 we can find nearly 30,000 so 300,000 samples each month. It means that like so 10,000 new Android malware applications per day. Of course, this is a big topic, especially for the information security, and there are two big different directions of how to detect Android malware. The first one is use the very traditional way, that is the signature-based way, and the other one is the machine learning-based way. Of course, I mean, the both of them have advantage and disadvantage. Many industrial products use the signature-based way, and also recently, in order to detect the many different variants of the famous Android malwares, we also use the machine learning-based way. On the other hand, with the development of the machine learning, there is also very important topic. The name is adversarial machine learning. So that means how how can we how can we do some research about the robustness and also the influence of the machine learning system and the attacks. That means the attacks the machine learning system. When we talk about the attacks the machine learning system, we mostly we talk about the different type of the situation. First one is the poisoning attack, which is mostly targeting to the training state. And the other way is the evasion state attack, which is mostly focused on the testing state. And also there are many different types of programs, like the fast branding based way and also the job map fraud based way. Here I will give some example like this image processing work. From the left side as a human being, we can see both from the left side and the right side, that is the pen, very fine pen. But if we give some noise in the middle with the adversary, which we call is adversary noise, the machine learning system will see this pen is not the real pen, that could be a jumbo with the 99.3% confidence. So that means the machine learning based classifier totally make a wrong decision. And also we also have this example which misclassified the stop symbol is the yard symbol, which means that we don't need to stop, it's the stop line. And also we also can make the classifier system make a mistake if we give some adversary noise to the number 8, which could be classified as the number 3. At the same time, we also have the same work in the text processing. For example, we change like just the sequence of the two letters in place under the head. Then the classify system will misclassify the positive review as the negative. Okay, until then, I will ask you some questions. For example, we can find about three machine learning algorithm samples in the text processing, image processing. How about in the machine learning based market detection system? Can we find also the algorithm symbols, algorithm noisy? So, the first question is, how about the robustness of the machine learning based market detection system and algorithm noisy? And the second question is, how can we construct this type of algorithm noisy? Means how can we modify the symbols and in order folding the machine learning based classifying to make it randomization. Okay, this is the reason why we call work is the monies. We want to, money. We want to manage we want to invent our machine learning based malware detection system in order to make the detection system in order to force the detection system to make a wrong decision. Here, of course, for the unusual malware detection system, we also can find many words which use the different type of the features. The first one we use the permission-based work. The other one we also use the structured information like the control graph, function call graph, data flow graph, and also the program fencing graph. I will give an example about the function call graph that work. First step, we use the function call graph, which is composed by several basic instruments like jet instruments, invoke instruments, moving instrument, test instruments, and also return instruments. And then we use the one-hot embedding embed our function to the one-hot embedder. Here like the 1010, and then we use the neighborhood hashing programs to embed our one node to embed our subgraph, which include multiple nodes to an embedder. We use the same function from this paper, and then we can do the feature embedding, which also transforms the boundary interpretation. Here, for example, we use the boundary interpretation of the 5,404, and then find the total number of the nodes with this embedding. And then at the second last step, we do our histogram extension. For example, in this situation, we have 11th. We have the 11th node with the embedding of the 5,404, and then we put the first 11 as the 1 and the other number is 0. Then last step, we put our embedded X into our classifier system and do the machine learning based malware detection. This is the basic idea of our Android malware detection system graph structure. Of course, here we also get the result from our previous mentioned Android malware detection system. We use two different thinking. The first one we use the histogram, and the other one we don't include the histogram extension. And the results of both of them are very similar. So until now we talk about our detection system. Then we will give our mathematical mode for the adversary samples. First of all, we should have the detection system. Of course, we talk about the detection system properly, and then we will get the loss function from this detection system. Use this loss function, we can construct our mathematical model for the adversary sample correctly. First of all, our purpose to do the adversary machine learning is maximize the loss function in order to classify, to make a wrong decision. Here we should, for the first step, we have the original graph, and then we do and get this GR standard as our modified graph, and GR is our original graph. And then our purpose is maximize the loss function. In order to get this purpose, in this paper we present two different ways. The first one is the instruction node, and the best idea of this method is finding the node which has the largest influence in the graph, and they inject those nodes multiple times in order to evade the malware detection system. And the second way is the gradient based way. So in this way, the first step we should calculate the gradient, and then we find the direction vector which has the same direction with the gradient. For the unstructured node, we should unstructured node we have the multiple steps. The first step is initialization. It means we should prepare the matrix which we can get from the training model, and then find the node which has the largest influence. In our situation, largest influence it means the node which has the minimal value. And after initialization, we can do our injection operation, which also have multiple steps. The first step, we should convert the digital representation of the instruction node to the binary representation, like we did in previously, like we convert the number 5,404 to binary expression, binary representation, and then we inject this binary representation in our neighbor hashing step, and also the feature embedding step, and also the histogram and the no histogram steps. And then we put the modified embedding into our graph, our classifier to test, to make a decision. That one is deny on measures. Of course, we also have some limitation. We also have some condition in order to use our instruction node. That is, our modified graph cannot have the very big difference with original graph. Okay, and then we will talk about our gradient-based way. In this way, we have three different recruitments. The first one is the accuracy of the graph node cannot be expressed less than 0. Of course, accuracy is the positive number. At least that will be 0, but that cannot be negative number. Secondly, we also in our histogram extension node, all 1 should be like the beginning of the vector. This requirement from the detection system. And the third one is we cannot reduce the numbers of original graph, because we cannot reduce the number of the node. Because that stands for the function. Because in our graph, that is a function called graph. The node stands for the function. If we reduce the node, it means that we reduce one function from the original application. That is logic. That will cause logic problem. And then after talk about the requirements, we will show our crafting method. Of course, as the first step, we should calculate the gradient with our object function, and also the gradient of the object function. After we calculate the gradient, we can get our direction vector, which has the same direction with the gradient. Like the graph A, we get our original gradient, but this gradient also includes some element which has the negative value. So we should do some adjust. The first step becomes our graph, which stands for the function, cannot include all of the elements. That means that we cannot one application cannot include all of the functions. So we should reduce some of the alignment in the direction vector by removing unrelated components. In this situation, we delete some elements from the subfield A, and then we move to subfield B. In subfield B, we also include negative element, which means the line 1, which is the left side. We should move this left side element into the right side because that means the positive. Yeah? And then the direction of our direction vector is changed, like the red line in our graph. In order to keep the direction of the red line from C and D, we should adjust the length of the line 2. In our situation, we prolong the line 2 times, and then we can get the same direction of the red line in figure D and the line in red line in figure A by the accuracy adjustment. This is the best way in our situation. After we do our grading vector adjusting, we will do our projection in order to meet the requirement 1 and B. 1, it means that we don't. Okay, until now we will talk about our evaluation. In our work, we use we calculate our dataset from the Androzone. We get 49,000 benign samples, and also we use the malicious sample from the deriving dataset, which includes 5,560 malicious samples. We divide our data into 5 folds in order to get the training dataset and also the testing dataset. We have the red box setting and also green box setting. Red box setting, it means that we can also access all the information for the training the model, and for the gray box, it means that we can access limited information for the target classifier, but we can also get another classifiers which trained by another folders. In our work, we have 5 different folders. And also in our work, we also can see the histogram extension and no histogram extension situation. First of all, we will show the result of the strongest node. In our work, we inject the strong node, which have the 1, 2, 3, 4, 5 different strongest nodes. Table 1 shows the strongest node with no histogram extension situation. In our work, we can see that we can get the nearly 72% misclassification rate with red box setting, but we doesn't inject like the 22% of the nodes. And also in the gray box, we can also get the nearly 80% misclassification, but in this situation, we just inject like 20.6969% nodes. Also get nearly 23 and 17 misclassification, 26 misclassification rate, just inject like 23 nodes, 23% nodes. From table A, we also can see that misclassification rate are very dependent on the number of the instructions. Again, we will test our work with the instruction node method and the histogram extension situation. In this situation, we can see that misclassification rate with histogram extension are significantly lower than no histogram extension. We can get like nearly 30% misclassification rate with red box setting. In this situation, we need to inject like the 37% of the node. And also another result we can get from table 2 and table A. Table 2 is red box attacking will get better misclassification than green box. Of course, in red box setting, we can get more information about the target training. Again, we will show our results about our results about our grading sum-based way. Here we give two different elements. The first one is alpha, the other one is threshold. Threshold. The purpose is threshold is limiting the number of the injected node. We will see our result in table 3. We will summarize the result here. That's if we inject one times node, it doesn't make any sense before. I mean, the one times node injection, it means that we totally change the behavior of the application. And with another setting, we will get nearly 14% misclassification rate and just inject like 70 from 17 to 14 node for 14 to 7 nodes. And also, yeah, in progress we talk about no histogram extension. And in histogram and the histogram extension with the gradient sum-based way, we also get the very good result here. This classification rates are significantly lower than no histogram extension, which is the same with the instructed nodes. And also the misclassification rates are around 20%. And the red box setting will have the better result than gray box setting. We also tested with the randomly chosen node injection, but in this setting we get very low successful in misclassification rate, like the percent. And here we also show our result in the figure. Okay, let us finish our talk with the conclusion. Here we talk about the malware detection of graph structure, and we use instructor node and the graph gradient-based way to construct our virtual noisy. Of course, our work has some limitation. So only emulate the counterflow graph, and also use the kernel